We are looking at limits. We're going to start with section 2.2, limit of a function. So what is the limit of a function? Basically, when we say let's investigate the behavior of the function f, that means let's investigate the y value. When we say behavior of the function, that's just a fancy way to say y coordinate, y value. This is the function for values of x near 2. So what's the y value doing when x is near 2? Well, we have a little chart. See, wouldn't want to take the time to write all that out. But we have a little chart that basically has x getting closer and closer to 2 from both sides. So it's getting closer from below 2, we call from the left on the number line. And then it's getting closer from numbers above 2 from the right on the number line. So x is approaching 2 in both directions here. And you can see that f of x, or y, is also approaching a value. What value is y approaching? It's approaching 4, isn't it? From both sides. So this is a good example of what it means to be a limit, that as x approaches a number from both sides, y is approaching a number from both sides. And that is what a limit is all about. Okay, so here's a picture of that function, and I hope you can see it. It's a parabola because it's x squared, and there's where as x is approaching from below 2 and above 2, the y is also approaching a value from both sides, the value of 4. Okay, and so we say the limit of the function f of x equals x squared minus x plus 2 as x approaches 2 is equal to 4. So that's how you say that. You say the limit of the function as x approaches 2, that arrow approaches, equals 4. And again, the limit is the y value. And here's another just way to write it, okay, with kind of horizontally with arrows. The y approaches a number, okay, remember 4 is the number, but in general L, as x approaches a number. Okay, so, and then it talks about it doesn't matter if x ever gets to the a value. It's okay if it doesn't get equal a. It just matters if x is near a. Okay, so here's some examples of functions, and here's some cases where f, the function f, has a limit at L. So right here, notice it's a smooth, continuous curve. There's no break. There's no little hole in the curve. So there you go. It has a limit at L as x approaches a. Notice here on this one, it has a hole there, right? So it doesn't, there's no value at L, okay? In fact, the value as x equals a, there is a value. It's defined elsewhere, right? It has a different y value. But does it still have a limit? And the answer is yes, it does. The limit is still here at L, okay? The limit is L still, even if there's a hole there. Okay, and then finally, there's no value at L. In fact, there's no value at A anywhere, right? F is not defined at A, is what we say. But again, it's okay. It still has a limit at L. So it's okay if it's there's nothing there, because it's still approaching L. Okay, one-sided limits, real quick. This is a piecewise function. Basically, this function on a graph would look like this. It's approaching 0 as t is less than 0. So it's basically crawling along the x-axis from the left side. And then it's approaching 1 from the right side as t is greater than or equal to 0. And there would be a dot here and then an empty circle here. Okay, so this function has two limits, two different limits, right? 0 and 1. And notice the notation here. When we see a little minus sign by the 0, and that means it's approaching 0 from the left. And we see a little plus sign. So again, this means the little minus sign means from the left, and the little plus sign means from the right. Okay, and then that's kind of what they're saying here. And what we call that, the limit as it approaches from the left, we call that the left-hand limit. If you see the little minus sign there on the A. And then the right-hand limit, if you see the little plus sign by the A. And here's another example of a function that, well, two different scenarios here. So this function has a left-hand limit only, and this function has a right-hand limit only. Okay. But the point here is that the function has a limit at L only if L, that same number, is the limit from the left and from the right. Okay, so they have to match up. And my pen just kind of died, so I have to charge it up. But that's what's happening right now. So just still getting used to pen management here. So anyways, those basically, if the left-hand limit and the right-hand limit are the same number, then F has a limit. And if they're not the same number, then F does not have a limit. Okay, so here we go. Here's an example. And I'm going to ask you basically, what is happening here? Okay, so the first one, it's super tall, it's super tiny, but here, x is approaching 2 from the left of this function. And can somebody tell me, just looking at the graph, what is the limit as the function is approaching 2 from the left? Yes, the answer is 3. The y value is up there at 3, even though there's an empty circle. Okay, next question. What's the limit as x approaches 2 from the right? Positive 1. Very good. And then the next question is, what's the limit at 2? It's right. That's kind of a trick question. There is no limit at 2. We say DNE does not exist for this. So again, I'll just write the answer here. This was 3, this was 1, and this is DNE. So this kind of questions you're having on your worksheet today, and maybe your quiz today. Okay, what about this? The limit as x approaches 5 from the left?
2.
Yes, it is 2. And what about as x approaches 5 from the right?
2.
It's also 2. It's okay if there's a little hole there. And finally, what is the limit at 5?
1.
Oh, the value of the function at 5 is 1, isn't it? There's a little dot there. So we would say g of 5 equals 1. But what about the limit? The limit is still 2. It's what's happening as x is getting close to 5. Just below 5, just above 5. That function value is super close to 2, isn't it? So it's okay that there's no value at 2. Okay, infinite limits. All right, so here we go. This is saying f of x approaches infinity as x approaches a. So a function can go up to infinity or to a negative infinity as x approaches a number. And here's a picture of a limit at infinity. Okay, so we have what's called a vertical asymptote right here. And the function value on both sides of a, so this is important, for there to be a limit, it has to go up to infinity on both sides for there to be a limit. So this is an example. We see this with rational functions. If like you have basically a function with like x minus a in the denominator, that's what's going to happen. Actually, in this case, it would be x minus a squared for it to go up to infinity on both sides. Alrighty. So, and then same thing here. You could have a limit at negative infinity, and this would be something like this, x minus a, but with a minus sign, like that. So there's a limit at negative infinity. And then here we have, these are one-sided limits. A function could just go up to infinity from one side and negative infinity from the other side. So let me just show you the pictures here. So, and this is common with rational functions. It'll go up to like either infinity or negative infinity just on one side. And maybe, so it won't necessarily have a limit. Okay, so now let's move on to 2.3, calculating limits using the limit laws. Well, there are some limit laws, and again, I'm glad I don't have to write all that down, but basically you have the limit of the sum of two functions equals the sum of the limits. And same thing for the difference of two functions, and then if you multiply a function by a number c, you can just c times the limit, and then the same with the product of functions equals the limit of the products is the product of the limits. And same with the quotient, number 5, only if g is not 0. So, you know, these are just things to use, not, you know, you don't have to memorize them. Okay. So, and then here, there's two, it says special limits. And what this is, just real quick, this is a horizontal line. This is a function, you know, f of x equals some number c. And basically, no matter where a is, a could be anywhere, it's always going to approach that number c. C would be right here, the value of the y on the y. And so, you know, when it's a flat line at c, it's always got a limit, right, at c. And then here's the function. The function itself is right here. And this is the function f of x equals x, where the x and y coordinates are the same. And so when x approaches, you know, like 2, the y value is also 2, right? So the limit, whatever number x is approaching, that's the number y is approaching. That's what it's saying. So this is a common occurrence. And so I just want you to understand what they're saying. And then here, basically what you're seeing here is we're substituting a in, right? You see x to the n, and now you see a to the n, right? And that's a common thing that we do when we're solving problems in this section. We end up just substituting a in there, and that's what they're saying here, direct substitution. If you have certain functions like polynomial functions, rational functions, you can just substitute in because a is in the domain. It's defined at a. It's okay to put a in the function. And it's okay that x doesn't equal a if there's a hole at a. Okay, so here's some more examples for us to go over. Okay, so a basically is saying, what's the limit of this combined function that we've made from adding f plus 5 times g? Basically, what we're going to do here is use the limit laws and do this. We're going to say, we're going to break it up into the limit of f plus 5 times the limit of g. This is what it means to use those limit laws. And so then we can just focus on the limit. Okay, so in other words, f is the pink line. What is the limit of f as x approaches -2? And this would be from both sides.
2, 1,
What's the y value as x approaches -2 of the pink line?
2, 1.
I hear a 2, I hear a 1.
Does not exist.
You say 1?
1.
And the answer is positive 1 because the y value of this point basically is 1. And that's what we're seeing. The y values are approaching 1. What about the limit of g, the blue line, as x approaches -2? Where's the y value?
-1.
Do we see -1? Yeah, down here, at that point, the y value is -1. So this is -1, and so this comes out to 1 plus 5 times -1. Okay, 1 minus 5. And so the answer to all that would be -4. But that's how you do it. You break it up into each limit using the limit laws. So we just take, because we don't have a function that's graphed here, that the function f plus 5g function is not graphed, but it's okay. We just take each part of it. All right, and then same thing here. We're basically, for letter B, we're just doing the product of the limits. The limit of f at 1 times the limit of g at 1. So let's do that. So what's the limit? I'll squeeze it in here. What's the limit of f as x approaches 1? Yes, up here it's, so that's a 2, and then times, what about g? Keep looking. That is dne does not exist. Does that make sense? Because we got two y values, one from the right, one from the left. And so the answer would be dne. In other words, if one part of it is dne, then the whole thing is. And finally, here, this is what we do here is we break it up into the quotient of the limits, and this is x approaching 2 and g. Okay, so all right, so we just take it one at a time. What's the limit of f, the pink line, as x approaches 2?
1.5.
Yeah? Tell me again, what's the limit as x approaches 2 of the f function? Why don't we just put that aside then, for now? Okay, thanks. Did somebody say 1.5? Yeah, basically. What about g? The limit? Yes, it is, crossing the x-axis, so it's 0. So what's happening there? What's our answer? Undefined, does not exist? Yes, for that reason. All right. So, and then it says, if a limit, if as x approaches a, if f is always this less or below the g, if the f function line is always below the g, then then the limit of f is below the limit of g. So the limit won't like jump up somewhere else. So it's all about what the behavior is when x is near a. And then the squeeze theorem, this is saying if both f and h have a limit at L, but g is between f and h, but f and h both converge to the same number, the y values both converge to the same number at L, then guess what? The g function that's always in the middle of those two functions, that will have to converge. So g gets squeezed, and here's an example. Okay, so here's h and f on the outside, and they have a limit at L. G in the middle has to have a limit at L. So that's called the squeeze theorem or the sandwich theorem. All right, so moving on. I know this is a lot, but and we will practice this on the worksheet. So yeah. So here we go. The precise definition of a limit. So this is section 2.4, and this gets into an area of math where we prove things. And basically, if you are a math major, which I don't expect most people here to end up as math majors, it's okay. But even if you go through the whole calculus sequence, a lot of people do that. Engineering people do that. All kinds of people do that. But then the math majors go beyond that. And what do they do after the calculus sequence? They what?
Linear algebra.
That's one of the things they do. Linear algebra, Well, actually, a lot of people do that too, the linear algebra, but like computer science people and that. The math majors go on to something called real analysis, where they basically prove the theorems of calculus. And now proofs are something that, like, you may have seen in a geometry class a while back, and the teacher usually doesn't want to deal with it, and so you may not have seen proofs at all. But that's what math majors start doing, and believe me, it's a shock to the system when you have to do that. You've been crunching numbers your whole life. You're like, I'm good at math because I can crunch numbers, and then you get into proving things, and there's not a lot of numbers, and there's a lot of symbols and stuff, and it's very abstract. And so I don't want to scare you off or anything, but it's different. Okay, and so this is just a little taste of what that is like. And so here it is in the calculus book. And so anyways, about 200 years ago, mathematicians said, hey, this limit stuff, it's nice that we just say x is close and y is close, but maybe we can get more precise in our language. And so this is kind of what happened here. So they're setting the scene here. Here's a function that's 2x minus 1 everywhere except when x equals 3, and then it's at 6. So here's the picture of that function. And basically we're saying f is going to have a limit at 3 when x is 3. Because if you put basically, if you graph the function 2x minus 1, it's right down here, as x goes to 3, that function is going to approach the number 5, right? If you put 2 times 3 minus 1 is 5, right? So we can see on the graph that a function is approaching, the y values are approaching 5, right? So, but they're saying, what does that actually mean for the y values to approach 5 as the x values approach 3? Well, it means that there's like a teeny little gap here on both sides of 5 when x has a teeny little gap, values within a certain interval down here next to 3. And we call this little distance here epsilon, okay, on both sides. And we call this little distance down here delta. So the Greek letters for D and E. So when x is within a distance delta of 3, the y is within a distance epsilon of 5. And that's what all this is saying. And so by taking x values close to 3, we can make the y values close to 5. Okay? And this is just another way of saying it. When x, in general, when x minus a is the number x approaches, delta is the tolerance, or it's within a certain tiny distance from a, then the y value will be within a certain tiny distance of the limit, like 5, within the distance epsilon. So I know it's kind of weird because suddenly we're bringing in Greek letters and stuff. But we're gonna do an example of this, kind of run through it, and it's gonna be on your worksheet and probably on your test. But it's a very simple example. And here's another way to say this, like to picture a function instead of an x and a y coordinate system. Think of a function as what we call mapping from one number line with x to another number line with f of x or y. And so it sends values from the left over to the right. That's what the function does. So if x is at 3, we saw the example here that the function value over here is 5. So if x is near 3, if a is near 3, then f of a will be near 5. Okay, so, and here's another way to put it. So if you start with a value in this little interval around a, or 3 or whatever number, then you're going to, okay, it's like in the military, if you have artillery, you're shooting some kind of gun, And you want to basically calibrate I don't even know what the word is, but you adjust, right, the settings of that. And so if it fires the projectile, it will land in a certain area, right? You have to kind of adjust, make an adjustment over here to have it end up over here. All right, so, and here's back to the XY plane. Here's another way to picture that. The Y value is just within this blue interval, okay? The function, see the function ends up squeezed within this blue interval when the X values are within this interval here. So again, if X is within this interval near A, then the Y values, or I should say down over here, the function values will be within this interval over here. And if I make that smaller, so if I make the interval around A smaller, that beige area, that's what you're going to see here, then I will be shrinking that epsilon, that blue area as well. I can get it more accurate, basically. Okay. And, okay, so, and then this says, this is just an example, but basically prove that the limit of this function 4x minus 5 is 7 when x approaches 3. And so we have, this is x, whoops, this is x minus, x is near 3, okay? Whoops, come on. X is near 3 when f of x is near the, the limit. What we do, and I just want you to kind of notice here, we start with f of x minus the limit, okay? And algebraically, okay, we just combine like terms right here. That's all we did, right? Combine like terms of -5 and -7. And then another algebraic step, we factor out a common factor. And we end up with, x minus a, x minus 3. So we start out with f of x minus L. We end up with the x minus a, x minus a. So just wanted you to notice that. And then what we do after that is we pick a delta, because what we're trying to do, and let me just go back to this slide here. What we're trying to do is find a tiny number delta that's tiny number that's the width of that, or half the width of that brown interval, so that when we put it into the function will project it into the near the y values, near the limit, near L basically. So for this function, because there is a 4, and let me just explain, because there's a 4 here, in general, the slope of anything, right, of a linear function, a straight line, do we agree the slope of a linear function is delta y over delta x, right? Which means that delta y equals m times delta x. And this is the m. Remember the function was 4x minus 5. So 4 was the slope of the function. So basically we're saying any change in y, which is, again, epsilon, equals m, 4, times delta, basically. And so we want to choose delta is epsilon over 4. We need to make that little x tolerance 4 times, or divide the, that's what will get it done, basically. Because the function magnifies any change along the x-axis, times it, multiplies it by 4, and that's how much change you're going to get along the y-axis. So when we put, so then we just run through this again. But the key step here is to replace the delta with epsilon over 4, so that you start with f of x, because what you're trying to prove here is that f of x minus L is less than epsilon, okay? You're trying to prove this. And so you create this chain that starts with this, f of x minus L, and it ends at epsilon. Do you see this whole chain here? How we started with f of x minus L, and we ended with epsilon, but we had this inequality sign along the way. So we're basically saying this right here, as what we get when we start out, f of x minus L is less than epsilon. That's what we're trying to prove. But we use this, that the fact that x minus 3 is less than delta along the way. I know it's a lot. And don't worry, we will have an example. It's just like learning a language, basically. So you don't have to be a math major, but it's just a little taste of that. Now, we're almost to the end of this section, and I think what I'm going to do is just like stop the recording. And so just to give you guys a mental break, give me a mental break. And then I just have one more section after that. But I know it's a lot to go straight through. So anyways, one more little thing here, and that is if a function is going up to infinity, remember that function that was going up to infinity on both sides of a number? What that means is that like if whatever number you pick, like 1,000 or 1,000,000, you say, well, when is that function greater than 1,000,000? And then what you do is you say, well, if I choose an x value close enough to the a, I can get that function to be as high as I want. I can make it over 1,000,000 as long as I keep squeezing in close to a. And here's the example. Okay, if I can get an x value within those yellow lines, then the function value will be above that number m, and I can keep just squeezing it in, and the function value will just be higher and higher and higher. So that's what it means to go to infinity. It means any number that you can think of, 1,000,000, 1,billion, 1,000,000,000,000, I can always make the function go higher than that, always, by choosing an x value that's closer to a, closer and closer and closer. And that's what it means to go to infinity.